Hello everyone, my name is Sajjad Akbar and I'm going to present you my separate paper with the title An Enhancement to Channel Access Mechanism for IEEE 802.15.3 millimeter 5G standard to support stringent quality of service requirement of Internet of Things. Other authors' names are also given, you can see. So this will be the layout of the presentation. I will start from motivation, introduction, background, problem statement, proposed solution, and result. So I tried to make it more simplified. So this is the huge motivation behind this research. Specifically, we want to cache Internet of IoT technologies for healthcare applications. So let me explain. Every year, millions of people die from fatal or chronic diseases, including cardiovascular, blood pressure, asthma, and diabetes. So what could be a best solution, best generic solution? Proactive wellness by providing early detection and prevention by using monitoring system. We should use our monitoring system in a way that patients get early detection, and so they will prevent from the diseases as well. Advances in low power and low cost IoT technologies have led to the solutions mature enough to use for healthcare. You can see IoT's application not only in the healthcare environment, but also in the other fields as well. Here you can see the sports, they have a huge role as well. Our main focus in this paper or in this research is towards healthcare applications which are associated with IoTs. So we are going to improve their performance by linking them with 5G network in the future. So brief introduction of IoTs. Obviously, IoT is considered as a system of interrelated computing devices, maybe hundred thousands, maybe millions, uses standard communication protocols and various access technologies. It is estimated at more than 30 billion IoT devices in 2025. So you can imagine maybe a huge part of IoT devices will be linked with healthcare applications. But you can imagine 30 billion is a huge number. If you have such a huge network, then it means such network will generate high volume of data, and that data will require time-bounded services plus reliable delivery services as well. Because for these IoT devices, one thing is very important. They don't generate huge packets. Usually they generate small packets in a quick interval. That creates a challenge. You need time-bounded services and reliable time-bounded services for them. There are different standards for IoTs. We will discuss some. IEEE 802.15.4 is one of the oldest standard. It came in 2007. Then they keep revising the standard. 802.15.6 wireless body area network. Zigbee is a consortium of different companies which agreed to use 15.4. 6LoWPAN, 6Dish, they are very prominent, and people are doing research work on those standards as well. 5G network is associated with cellular, usually associated with cellular network, which is actually not very true, because we have application of 5G network not only for cellular network, but also for standalone personal and local area network as well. In the future, even you can still find a lot of such devices where you are using 5G network or 4G network in a local and a personal area network. So that's why it is important to discuss the protocols which are working under those standards and how we can improve those protocols as well. FP7 project Metis for 5G incorporates 5G with IoTs to take advantage of this gigabit network. Now, another point came, gigabit network. So it means if we are using 5G, we are going towards gigabit network. How? Okay, I will explain. Due to spectrum, okay, 5G will use millimeter wave. So it is one of the potential candidate for 5G by providing data rate up to gigabits per second. It uses spectrum between 30 to 300 gigahertz from the figure you can see, and the wavelength between 10 mm to 1 mm. So you can see this is a spectrum for 5G. There have been several standardization activities for millimeter wave in the 60 gigahertz band. So here in this range, so people are also focusing on 60 gigahertz band. You can see unlicensed. Why? Because it is more suitable for human bodies and for certain application. That's why people are working on this under, and people are considering these standards as well nowadays. So keep this in mind. Our focus is not on cellular network for 5G in this research. We are focusing on standalone and personal area network of 5G. That's why we are discussing this. So this is the diagram of a network under 15.3C. You can see a coordinator is there, a central body, we call it personal network coordinator is there. And all these nodes are connected through your personal coordinator. So personal coordinator will decide whom data should send to whom. Another important thing here is because and this PNC works under 60 gigahertz. This we also call it Piconet. You already heard about Piconet in 15.4. This is Piconet for 15.3C. Because they are sharing the single channel, so it means they need a channel access mechanism to send their request to coordinator. Then coordinator will allot them a slot to do the data transmission. You can see here. First, they will request to coordinator, then coordinator will give them a slot where they will transfer the data. You can see here from B2 to B1. Usually, this standard work under a superframe. We use the term superframe. Superframe is a time interval where you can see in superframe is divided in different intervals. Especially, you can see contention access period. See a cap. We call it cap as well. In cap, all the nodes, they try to access the channel. They compete and they try to access the channel. Whoever gets the channel will successfully send the request. So this is the general mechanism for this standard. What is the problem then? Everything is fine if no, there is an issue. Because I told you the focus of this research is specifically for medical scenarios. For example, where a patient is equipped with multiple sensors, all those sensors which are basically IoT, an IoT device, wireless IoT device, they are getting some information and they are sending to the coordinator. So we are considering that scenario as well. So what's happening? After successful delivery of CTA request, we discuss this. The issue is there is no guarantee that a node will get a channel in the contention process in the existing standard. And why we want to use existing standard? Because it provides high throughput and very less delay. So we want to get benefit, because in the future in medical standard, there will be hundred thousands of nodes connected to a hospital or to anybody. So there we need a standard which can deal with these challenges in terms of throughput and delay. Again, imagine this diagram. Oh, it will come after. Yes, you can. This is the problem statement. You can think of problem statement like this. You have multiple sensors. Here you can only see 9 devices, but there could be hundred thousands of devices which are generating frames in different rates. Like after 4 milliseconds, ECG is generating its frame, EMG is generating after 6 milliseconds. So each of them are generating their frame in a different time interval. Plus, they require different throughput and different delay values. Otherwise, these frames will not be meaningful when it will reach to application after a certain delay. So there is a time-bounded issue is involved here. If you can't deliver this in a limited time, then these frames are useless. So this is a big challenge. In the current standard, you have to compete for the channel access. If you are not getting channel access, if it means you are queuing your packets, and those packets will be useless if you send them, even if you send them in future. So this is the main problem. Let's go towards the solution. First, I will discuss the contributions. There are multiple contributions. I discussed few of them here. First, we propose a numerical model of a contention access period using under this standard 15.3C. Why we need a numerical model or analytical modeling? Because first we need to understand the standard and we need to identify the worst case scenario for this standard. And then we need to map it with our application, which is related to medical scenarios. They have limited delay and throughput values. So first we need to understand and we need to identify the worst case value. That's why we developed this model. It was not there before. 15.3C analytical model was not there. So we developed this model. Then we propose a priority-based mechanism with 3 priority classes: high priority, low priority, and medium priority. These priorities are set with contention window values. If you are not aware with the contention window, you can go through my paper. You will understand contention window. What is the purpose of contention window values? Okay. Analytical modeling or the numerical modeling of CAP was done for end-to-end delay, throughput value, for end-to-end delay, and to get throughput values, especially for the worst case and the best case. These are some snapshots from the research paper. I will recommend you should go through my paper to further understand these equations. Overall, you can see we are calculating end-to-end delay, and end-to-end delay is calculated based on the delay in the transmission of the frame plus acknowledgement plus channel access time. All these time are included in end-to-end delay. I also included the specification of this standard. I didn't add all the equations, but you can find more equations for this analytical model in my research paper. So I told you we propose to use priority mechanism for IEEE 802.15.3C. And in this priority mechanism, we introduced 3 priority classes: low, medium, and high. Let me map them here. For example, ECG, we will assign it as a high priority because it needs very frequent. It is generating packets after 4 milliseconds, generating frames. So it means, and it is also critical. ECG values could be critical for a patient. So we will assign high priority values, and maybe you can see for blood glucose or temperature, we can assign low priority value. Even we cannot, even if you don't want to assign priority value, that's fine. Because even if you receive temperature and glucose values maybe after 5 minutes, that will be okay. But for these critical, you need to assign maybe ECG will be high, EMG will be medium priority. I told you these priorities are assigned with the contention window range, and the details are given in the paper. So propose priority mechanism node with minimum contention window value gets the higher priority, and the vice versa. We implemented this in NS2, another simulator, and we got the results as well. We also got the same results, almost the same, not the same. There's a slight difference in the numerical modeling. Like we did the numerical modeling of different scenarios, mathematical modeling, and we got those values and we verified those values in the simulator as well. For performance evaluation, we looked for delay, throughput, and bandwidth. So you can see these 3 graphs. First graph is of throughput. You can see high priority. And for high priority, you can see you are getting a good throughput. The blue color shows the packet size with 32 bytes, 64, 96, and yellow 138. If you are keep increasing your packet size, your throughput is increasing. Okay, but for medium priority, low priority, and low priority, you can see we have lower values. So it means you will get good result for high priority, medium priority, and low priority values. This is for the delay, which is an important factor. You can see for the high priority, delay start from maybe around 35 microseconds, which is very acceptable for these devices, and it's keep increasing with the increase of packet size. So packet size also has impact on the transmission or on the delay. But good thing is these IoT based devices, they generate small packets, but in a huge number. For medium priority and low priority, you can see the values. Details of these graphs are given in the paper. These are the results for retransmission. For example, if you transmit a packet, it is not delivered, you need to retransmit that packet. Okay, so after doing 3 retransmission, we assumed a packet is not delivered for 2 times, so you are doing 3rd retransmission. So you can see after 3rd retry, which is gray, in the high priority, still you are at acceptable level. in medium priority, still you are at acceptable level. So we have proposed such a priority mechanism and settle the contingent video values in a way that you are getting acceptable values. There are more graphs, but I added few. So I will conclude. A prioritized channel access mechanism is proposed and is an enhancement to 15.3, which is a 5G based standard for standalone and personal area network. Don't mix it with the cellular network. And we enhance the cap mechanism by introducing a priority based mechanism. We did implement, we got the results from mathematical modeling, and plus we verified them in the simulator as well. Comparative analysis show we have very good results for specifically for the medical application, because the focus of research in the motivation we discussed, we are looking for the medical status in the future, where we are going to use IoT devices for healthcare monitoring, and we are going to link those IoT devices for medical domain with 5G network. So if we will link successfully link it with the 5G network, we will get benefit of the 5G network for medical status, especially in terms of delay and throughput. So you saw our proposed scheme performed well and showed that very promising results. I hope it was a very useful presentation. If you have any question, you can ask me after the presentation, or you can send me, or you can email me on my email ID, so we can discuss. And we are also trying to extend this further as well, this research, because there's a huge motivation of for such diseases which are fatal actually for human beings. Thank you very much. Any questions